For the first iteration, because 3 smaller equilateral triangles are being added, the equation for the total area becomes the following. We already know that the area of the initial triangle is root 3 times s squared over 4, where s is the initial length of one side. And we add 3 smaller triangles with side length 1/3 of the original. And simplifying the equation results in root 3 over 4 times s squared times parentheses 1 plus 3 over 9. For the second iteration, because 12 even smaller triangles are being added, the equation for the total area becomes the following. We start out with first iteration's area, and we add 12 more even smaller triangles with side lengths 1/9 of the original, and thus we get this final equation. The third iteration includes 48 even smaller equilateral triangles, so the equation for the total area becomes the following. Here we start out with second iteration's area and include 48 even smaller triangles with sides length 1/27th of the original. Simplifying the equation results in this equation. Root 3 over 4 times s squared times parentheses 1 plus 3 over 9 plus 3 times 4 over 9 squared plus 3 times 4 to the squared over 9 cubed. By now, the pattern should be clear. The red circle is the number of additional triangles at kth iteration, and the green circle is the area of each additional triangle at kth iteration. The blue circle is the total area of the additional triangles at kth iteration. This means that in order to get the area at kth iteration, we must add total marginal area at kth iteration to the total area at k minus 1th iteration. Hence, after nth iterations, we get the area to be the following. Root 3 over 4 times s squared times parentheses 1 plus sigma notation from k equals 1 to n, 3 times 4 to the k minus 1th power over 9 to the kth power. In this equation, the sigma notation represents the fact that we added the area of every possible additional triangle until k minus 1th iteration. The green circle represents the partial sum of a geometric series with ratio r equals 4 over 9. Since the geometric ratio is less than 1, the sum converges as n goes to infinity. Therefore, we see that the area of koch snowflake is the following. The sigma notation we see in this equation can be eradicated by using the infinite geometric series equation, a first over 1 minus r. The first term appears when k equals 1, and it is 3 over 9. Since a1 is 3 over 9, and the ratio is 4 over 9, we can simplify the equation to 3 over 9 over 1 minus 4 over 9, and thus the whole equation can be ultimately simplified to 2 root 3 times s squared over 5. If you put s equals 9 in the equation and in your calculator, you will notice that the area of the koch snowflake to an infinite extent is a finite number. 162 times root 3 over 5 is approximately 56. Now, let's compare our initial guesses for the perimeter and the area of koch snowflake. Does your guess match the real outcome? Mine actually was different. I initially thought that the perimeter and area both would stop at a certain number. However, now we know that I was wrong. The area does stop at about 56, but the perimeter goes to infinity. I really hope you enjoyed watching this video and learned a bit more about koch snowflake.
Created using Powtoon.